Right now, something extraordinary is happening in the depths of space that defies everything we thought we knew about how our cosmos works. For decades, astronomers have studied comets as passive victims of solar radiation, ice and rock melting helplessly as they approach our star. But what if we had it backwards this entire time? What if, instead of the sun dictating the fate of these ancient wanderers, a visitor from another star system could actually influence our sun itself? The date is October 15th, 2025, and in just 6 days, on October 21st, something unprecedented will occur. Comet 3I Atlas, that mysterious traveller from the void between stars, will slip behind our sun in what astronomers call solar conjunction, disappearing from our view for 8 critical days before reaching Perihelion on October 29th. But here's what's keeping researchers awake at night. What's making veteran astronomers question 40 years of established science. The mounting evidence suggests this interstellar visitor isn't just being shaped by our sun's influence. It might actually be affecting solar behavior in ways we never imagined possible. Think about that for a moment. A chunk of ice and rock, barely a few kilometers across, born under the light of an alien star potentially millions of years ago, could be influencing the very source of energy that powers all life on Earth. The implications are staggering, and the scientific community is scrambling to understand what this means for everything we thought we knew about stellar physics. Dr. Elena Rodriguez at the European Space Agency first noticed the anomaly 3 weeks ago while analysing coronal hole activity patterns. These are regions where the sun's magnetic field opens up, allowing solar wind to escape at higher speeds, and they're typically random, chaotic phenomena that follow the sun's own internal magnetic cycles. But Rodriguez discovered something that made her run the calculations 5 times before she trusted the results. The timing and positioning of these coronal holes weren't random at all. They were correlating precisely with 3I Atlas's trajectory as it approached our solar system's heart. "It's impossible," she told her colleague during a late-night video call that I managed to obtain recordings of. "Comets don't influence stellar magnetic fields. The mass ratios are absurd. It's like saying a grain of sand could redirect a freight train, but the data doesn't lie, and what the data shows is a pattern so clear that even the most skeptical scientists are starting to pay attention. The phenomenon began subtle, almost imperceptible, when 3I Atlas was still beyond the orbit of Mars. Solar wind monitoring stations detected minute fluctuations in magnetic field strength that seemed to pulse in rhythm with the comet's approach. At first, researchers dismissed these as instrumental noise, cosmic background interference, the usual suspects when dealing with measurements at the very edge of detectability. But as weeks passed and the comet drew closer, the fluctuations grew stronger, more defined, impossible to ignore. By early October, when 3I Atlas had closed to within 50 million kilometers of the sun, something extraordinary was happening in the corona. The normally chaotic, turbulent outer atmosphere of our star began showing organized structures, streams of plasma that aligned themselves along invisible magnetic highways that seemed to point directly towards the approaching interstellar visitor. Solar physicists have never seen anything like it. The sun, our massive, nuclear-powered star, appeared to be responding to the presence of this tiny cosmic wanderer in ways that challenge our fundamental understanding of how gravity, magnetism, and plasma interact on astronomical scales. But here's where it gets truly unsettling. The effects aren't limited to subtle magnetic field variations or plasma stream alignments. Ground-based observatories have detected unusual radio emissions from the sun's surface, frequencies that correspond to no known solar phenomenon, broadcasting in patterns that pulse every few hours in perfect synchronization with 3I Atlas's orbital period. It's as if our star is trying to communicate with this visitor from another world, or perhaps it's being forced to respond to signals we can't yet understand. The timing couldn't be more critical. In just 6 days, on October 21st at 14:23 Universal Time, 3I Atlas will pass directly behind the sun as viewed from Earth, entering solar conjunction and vanishing from our telescope's view for 8 days. During this crucial period, When the comet faces the full fury of solar radiation at its closest approach, we'll be blind to whatever interaction is taking place. The greatest cosmic mystery of our generation will unfold in darkness, hidden behind the very star it might be influencing. What makes this even more extraordinary is the scale of what we're witnessing. The Sun contains 99.86% of all matter in our solar system, its mass so enormous that it bends space and time around itself, creating the gravitational well that holds planets, asteroids, and comets in their eternal dance. For something as small as 3I Atlas to influence such a massive object should be physically impossible, according to everything we understand about celestial mechanics. Yet the evidence continues to mount with each passing day. NASA's Solar Dynamics Observatory has been tracking what mission scientists are calling sympathetic resonance patterns in the Sun's magnetic field lines. These are synchronized oscillations that appear to mirror 3I Atlas's approach trajectory, as if the Sun's magnetosphere is somehow entangled with the comet's own magnetic environment. The phenomenon is so unprecedented that a team of theoretical physicists at MIT has proposed an entirely new model of interstellar object interaction that involves quantum field effects operating on macroscopic scales. The implications extend far beyond academic curiosity. If a single interstellar comet can influence solar behavior, what does this mean for the millions of similar objects drifting through our galaxy? Are stellar systems more interconnected than we ever imagined? Could the Sun's activity, which directly affects Earth's climate, magnetic field, and technological infrastructure, be influenced by visitors from distant stars on a regular basis without us ever realizing it? As 3I Atlas approaches its October 21st conjunction date, astronomers worldwide are racing to gather every possible piece of data before the comet disappears behind our star. Ground-based radio telescopes are monitoring continuously. Space-based observatories are adjusting their schedules to focus on this unprecedented event. And even amateur astronomers with backyard equipment are contributing to what may become the most important observational campaign in modern astronomy. But here's what's truly keeping scientists awake at night: the growing realization that this might not be an isolated incident. Deep archive searches through decades of solar activity data are revealing subtle patterns that correlate with the perihelion passages of other long-period comets, signatures so faint they were invisible until researchers knew what to look for. The possibility is emerging that comets have been influencing solar behavior throughout human history, their effects so subtle and long-term that we attributed them to natural solar cycles. The questions this raises are profound and disturbing. How many unexplained solar phenomena throughout history might have been caused by interstellar visitors we never detected? How many technological disruptions, climate variations, or magnetic field changes on Earth were actually the result of cosmic interactions we didn't understand? And most importantly, what will happen when 3I Atlas reaches its closest approach to the Sun on October 29th, traveling at 68 kilometers per second while completely hidden from our view? Right now, behind the Sun, where we cannot see, forces are building toward a confrontation between matter from another star system and the nuclear furnace that powers our world. In just 6 days, we'll lose sight of 3I Atlas as it enters the most dangerous phase of its billion-year journey. What emerges from behind the Sun in early November might be a fragmented remnant of its former self, or it might be something else entirely, forever changed by an interaction we're only beginning to understand. The countdown has begun to the most important 8 days in astronomical history, when the Sun and a visitor from the stars will dance together in darkness while humanity waits, blind and breathless, to discover what mysteries unfold in the light of another world's child meeting the fire of our own. October 21st, 2025, 1423, Universal Time. Mark that moment in your mind, because it represents the beginning of 8 days that could rewrite our understanding of how the universe works. At precisely that second, from Earth's perspective, Comet 3I Atlas will slip behind the Sun's blazing disk and vanish from human observation, entering what astronomers call solar conjunction, a cosmic game of hide and seek where the most important player disappears just when the action reaches its peak. The geometry of this celestial alignment is both beautiful and maddening. Picture Earth, the Sun and 3i Atlas forming a perfect straight line stretching across 150 million kilometers of space, with our star sitting directly between us and the most fascinating object to visit our solar system in recorded history. For 8 agonizing days, every telescope on Earth, every space-based observatory, every amateur astronomer with a backyard setup will be rendered utterly blind to whatever drama unfolds in the corona's blazing embrace. But here's what makes this conjunction different from any other in astronomical history. We're not just losing sight of a typical comet following a predictable path around our sun. We're about to lose contact with an interstellar messenger, a chunk of ice and rock that formed in the disk of another star, potentially millions of years ago, carrying within its frozen heart the chemical signature of an alien solar system. And we're losing sight of it at the exact moment when its interaction with our sun appears to be reaching unprecedented intensity. The timing is almost cruel in its precision. 3i Atlas will emerge from behind the sun on October 29th, reaching perihelion at exactly 11:47 Universal Time, when it passes just 1.36 astronomical units from our star's surface. That's roughly 204 million kilometers. Closer than the average distance between Earth and the Sun, close enough for the comet to experience solar radiation intensity nearly 4 times stronger than what Earth receives. At that moment, traveling at an incredible 68 kilometers per second, 3i Atlas will face the full fury of stellar fire while completely hidden from our view. Think about the cosmic irony. After waiting potentially millions of years for an interstellar visitor to provide us with clues about other stellar systems, after detecting only 3 such objects in all of human history, we're about to lose sight of the most active and mysterious one during the most critical phase of its journey. It's like being handed the Rosetta Stone of interstellar science, and then having it locked in a vault just as you're about to decode its most important message. The mathematics of solar conjunction are unforgiving. When an object passes behind the sun from Earth's perspective, it doesn't just become difficult to observe, it becomes completely impossible. The sun's electromagnetic radiation overwhelms every detector, its gravitational field bends and distorts any signals, and its magnetic field creates interference that renders even radio contact impossible. For those 8 days between October 21st and October 29th, 3i Atlas might as well exist in another dimension. But what's keeping astronomers awake at night isn't just the observational blackout. It's the growing realization that this conjunction period coincides exactly with the most intense phase of whatever interaction is occurring between the comet and our sun. The coronal hole formations that have been tracking 3 Atlas's approach, the synchronized radio emissions, the magnetic field fluctuations, all of these phenomena are building toward a crescendo that will occur precisely when we're blind to observe it. Dr. Sarah Chen at the Mauna Kea Observatory has been tracking the build-up with growing anxiety. It's like watching 2 dancers approach each other across a cosmic ballroom, she told me during our interview last week. The music is building. The rhythm is accelerating, and just as they're about to touch, someone turns off all the lights. We know something extraordinary is going to happen, but we'll only see the aftermath. The cruel mathematics of orbital mechanics mean this conjunction was inevitable from the moment 3i Atlas entered our solar system. The comet's hyperbolic trajectory, its speed and angle of approach, all conspired to create this perfect alignment, just as the interstellar visitor reaches its closest approach to our star. There's no technology that can see through the sun, no observational trick that can peer around its edge during those critical 8 days. What makes this even more frustrating is the realization of how much we're going to miss. Computer models suggest that October 29th, the day of perihelion, will mark the peak of 3i Atlas's water production as solar heating vaporizes the comet's ancient ice at maximum rate. This outgassing creates the comet's characteristic tail and coma, but more importantly for our mystery, it generates the ionized plasma that might be creating the magnetic field interactions we've been detecting. The European Space Agency's models predict that during perihelion, 3i Atlas could be losing mass at a rate of several tons per second, ejecting water vapor, carbon dioxide and organic compounds at speeds of hundreds of meters per second. This creates a temporary atmosphere around the comet nucleus, a mini magnetosphere that could interact with the sun's magnetic field in ways we've never observed. And it's all happening while we're completely blind to the process. Perhaps most tantalizingly, the 8-day conjunction period coincides with a predicted maximum in solar activity for this solar cycle. Solar physicists have been tracking the buildup of magnetic energy in the sun's corona, and their models suggest that late October 2025 could see significant solar flare activity, coronal mass ejections, and magnetic field reconfigurations. The possibility that these solar phenomena might be somehow connected to 3I Atlas's presence is both scientifically fascinating and deeply unsettling. The international astronomical community has been scrambling to position every available resource for maximum coverage of the pre-conjunction and post-conjunction periods. NASA has repositioned the Parker Solar Probe to gather data from the comet's solar wind interaction region. The European Space Agency has coordinated observations from multiple Mars orbiters to capture the comet from different angles, and ground-based observatories worldwide have cleared their schedules for continuous monitoring right up until conjunction begins. But there's a deeper mystery buried in the timing of this event. Mathematical analysis of 3I Atlas's trajectory suggests that its entry into our solar system wasn't random. The comet's path, its speed, and its angle of approach create what orbital dynamicists call a gravitational keyhole trajectory, one that maximizes its interaction time with our sun while minimizing the energy required to escape our solar system afterward. It's almost as if this interstellar visitor was deliberately aimed to create the longest possible period of solar interaction. The implications are staggering. If 3I Atlas's trajectory was somehow intentional, if it represents more than just a random chunk of ice wandering between the stars, then its conjunction period takes on an entirely different meaning. Instead of an unfortunate observational gap, it becomes a carefully orchestrated rendezvous between matter from another star system and our own sun, a cosmic appointment scheduled millions of years in advance. As October 21st approaches, astronomers are racing to gather every possible piece of data before the blackout begins. Radio telescopes are monitoring the increasing intensity of unusual solar emissions. Optical observatories are tracking the comet's brightening as it approaches perihelion, and space-based instruments are measuring magnetic field fluctuations with unprecedented precision. Every data point collected now might be crucial for understanding what happens during those 8 lost days. The countdown has become personal for everyone involved in this research. Rodriguez at ESA hasn't slept more than 4 hours a night for the past week. Dr. Chen has moved a cot into her observatory office, and amateur astronomers worldwide are organizing around-the-clock observation schedules to capture every moment before 3I Atlas vanishes behind our star. But perhaps the most unsettling aspect of this approaching conjunction is the growing realization that we might not recognize what emerges on the other side. Comets can fragment under intense solar heating, their nuclei splitting into multiple pieces that follow slightly different trajectories. If 3I Atlas breaks apart during perihelion, we might find ourselves tracking not one mysterious interstellar visitor, but several, each carrying pieces of the original cosmic puzzle scattered across different paths through our solar system. The 8 days of darkness are coming, whether we're ready or not. On October 21st at 14:23 Universal Time, humanity will lose contact with the most important cosmic visitor in our history, just as it enters the most dangerous and mysterious phase of its billion-year journey. What happens next will unfold in the hidden fire behind our sun, where matter from another world meets the nuclear furnace that powers our own, and we can only wait in darkness for whatever emerges from that stellar crucible. The first hint that 3I Atlas was unlike any comet we'd ever encountered came from an observation so extraordinary that the scientist who made it thought his equipment was malfunctioning. Michael Torres at NASA's Swift Observatory was conducting routine spectroscopic analysis when his instruments detected water vapor production rates that defied every model of cometary behavior ever developed. The numbers were so extreme that he ran the calibration sequence 3 times before accepting what the data was telling him. "It's spewing water like a fire hose on full blast," Torres wrote in his initial report, a phrase that would become legendary in astronomical circles. But even that vivid description understates the magnitude of what 3I Atlas is doing to itself as it approaches our Sun. The comet is losing water at a rate that's not just unusual for an object of its size, it's physically impossible according to our understanding of how frozen volatiles behave under solar heating. To understand why this is so unprecedented, you need to grasp the delicate balance that governs normal cometary behavior. When a typical comet approaches the Sun, solar radiation gradually heats its surface, causing frozen water to sublimate directly from ice to vapor without becoming liquid first. This process should be relatively gentle and predictable, controlled by the amount of solar energy hitting the comet's surface and the thermal properties of its nucleus. It's a process we've observed hundreds of times, a cosmic dance as old as the solar system itself, but 3I Atlas is rewriting the rules. Instead of the gradual, controlled water loss that characterizes normal comets, this interstellar visitor is experiencing what can only be described as explosive outgassing. The Swift Observatory's measurements indicate water production rates exceeding 10,000 kilograms per second, a number so staggering that it would drain a comet nucleus the size of 3I Atlas in a matter of weeks if sustained. Yet somehow, impossibly, the outgassing continues to intensify as the comet draws closer to the Sun. The implications are profound and disturbing. For 3I Atlas to maintain such extreme water loss rates, its internal structure must be fundamentally different from any comet we've studied. Traditional comet nuclei are often described as dirty snowballs, relatively uniform mixtures of ice, dust, and rocky debris held together by gravity and the natural cohesion of frozen materials. But the behavior of 3I Atlas suggests something far more complex, perhaps layered internal structures with vast reservoirs of subsurface ice connected by networks of fractures and cavities. Sarah Yamamoto at the Japan Aerospace Exploration Agency has proposed a radical model to explain what we're observing. She suggests that 3I Atlas might contain what she calls pressure chambers, internal voids, where volatile materials accumulated over millions of years of interstellar travel. When solar heating penetrates the comet's outer layers, these chambers could rupture in sequence, each breach releasing massive quantities of water vapor in sudden violent bursts. Imagine a champagne bottle that's been shaken for 1,000,000 years. Yamamoto explained during a recent conference call, "When you finally pop the cork, the release isn't gentle or controlled, it's explosive, and it continues until all the pressure is relieved." The analogy is both elegant and terrifying when you consider that we're talking about an object traveling at interstellar speeds while literally tearing itself apart. But the mystery deepens when you examine the composition of this extraordinary outgassing. Spectroscopic analysis reveals that the water vapor streaming from 3I Atlas contains isotope ratios, unlike anything found in our solar system. The deuterium to hydrogen ratio, a crucial fingerprint that reveals the formation conditions of water ice, indicates temperatures and pressures that could only exist in the disk of a forming star. Very different from our own Sun, this alien water, born under the light of another star perhaps millions of years ago, is now erupting from 3I Atlas at rates that create their own local weather system. The massive water production generates a coma, the glowing cloud of gas and dust that surrounds the comet nucleus, extending over 100,000 kilometers in diameter. That's nearly the distance from Earth to the Moon, a temporary atmosphere created by the violent death throes of ancient ice formed in another stellar system. What's even more remarkable is how this extraordinary outgassing might be affecting the space environment around the comet. When water vapor is exposed to solar ultraviolet radiation, it breaks down into hydrogen and oxygen atoms that become ionized, creating a plasma environment around 3I Atlas. This ionized gas can interact with magnetic fields, both the Sun's and any generated by the comet's own activity, potentially creating the electromagnetic phenomena that astronomers have been detecting. The physics of this process are staggering in their complexity. As water vapor erupts from 3I Atlas at thousands of kilograms per second, it expands rapidly in the vacuum of space, cooling and condensing into tiny ice crystals that reflect sunlight, creating the visible brightness we observe from Earth. But simultaneously, solar radiation is ionizing this expanding cloud, creating a temporary magnetosphere around the comet that could extend millions of kilometers into space. Dr. Elena Kowalski at the Max Planck Institute for Solar System Research has calculated that the magnetic field generated by 3I Atlas's ionized coma could be strong enough to deflect the solar wind, creating a bow shock similar to what we observe around planets like Earth and Mars. "We're not just looking at a comet anymore," she told me during our interview. "We're looking at a temporary magnetic obstacle in the solar wind, a moving disturbance that could influence space weather throughout the inner solar system. The energy required to sustain such massive water loss is almost incomprehensible." Conservative estimates suggest that 3I Atlas is currently dissipating energy at a rate equivalent to several nuclear power plants, all generated by the simple process of ice sublimating under solar heating. But the comet's internal structure must be channeling and concentrating this energy in ways we don't understand, creating the explosive outgassing that has stunned the astronomical community. Perhaps most unsettling is the realization that this water production rate is still accelerating. As 3I Atlas draws closer to the Sun, approaching the October 29th perihelion date, spectroscopic measurements show that the outgassing continues to intensify. If current trends continue, the comet could be losing water at rates exceeding 50,000 kilograms per second during its closest approach, enough to fill an Olympic swimming pool every few minutes. The visual impact of this phenomenon is becoming apparent even to amateur astronomers. Photographs of 3I Atlas taken over the past month show a comet that's brightening exponentially, its tail extending further into space with each passing day. The tail itself, composed primarily of water vapor and ice crystals, now stretches over 10 million kilometers behind the comet, a ghostly river of alien water flowing away from our sun. But here's where the mystery becomes truly mind-bending. Computer models of cometary outgassing predict that an object losing water at the rates observed from 3I Atlas should have exhausted its volatile inventory long ago. The fact that the outgassing continues and even intensifies suggests that we're dealing with an object whose internal structure and composition challenges our fundamental understanding of how comets form and evolve. Some researchers are beginning to wonder if 3I Atlas might not be a traditional comet at all, but rather a different class of object entirely. The possibility has been raised that we're observing the breakup of a small icy moon or planetary fragment, something with internal differentiation and complex subsurface structures that could contain vast reservoirs of frozen volatiles. If true, this would make 3I Atlas not just an interstellar visitor, but potentially a piece of another world, a fragment of an alien planet that somehow escaped its home system and wandered the galaxy for eons before finding its way to our sun. As October 21st approaches, and 3I Atlas prepares to disappear behind the sun, the water production continues to build toward what promises to be an explosive climax. The 8 days of solar conjunction will coincide with peak solar heating, maximum outgassing rates, and the highest probability of nucleus fragmentation. When the comet emerges from behind our star in early November, it might be fundamentally changed, its ancient structure finally succumbing to forces that have been building for millions of years. The fire hose of alien water continues to blast into space, carrying with it the chemical history of another star system, while simultaneously creating electromagnetic phenomena that might be influencing our own sun. In just 6 days, this extraordinary display will move behind our star and reach its most violent phase, hidden from human observation, but potentially reshaping our understanding of how matter behaves when visitors from the depths of space encounter the nuclear fire that powers our world. The revelation came at 3:47 a.m. on October 8th, when Dr. James Patterson at the National Solar Observatory was reviewing overnight magnetogram data. and discovered something that made him question 40 years of solar physics expertise: the sun's magnetic field lines, those invisible highways of force that normally writhe and twist in chaotic patterns driven by internal dynamo processes, were showing organized structures that pointed directly toward 3I Atlas, like iron filings aligning with a powerful magnet. "It's impossible," Patterson muttered to himself as he zoomed in on the data, adjusting contrast levels and running diagnostic checks on his instruments. But the evidence was undeniable. Stretching across millions of kilometers of the sun's corona, magnetic field lines were organizing themselves into coherent streams that tracked the comet's position with unprecedented precision. The sun, our massive nuclear furnace containing 99.86% of all matter in the solar system, appeared to be responding magnetically to a tiny chunk of ice and rock barely a few kilometers across. To understand why this defies everything we know about cosmic magnetic interactions, you need to grasp the tremendous scale disparity we're dealing with. The sun's magnetic field is generated by the movement of electrically conducting plasma in its interior, driven by rotational forces and convection currents that involve more matter than exists in all the planets combined. For an external object as small as 3I Atlas to influence this system would be like expecting a grain of sand to redirect the flow of the Mississippi River. Yet the data doesn't lie, and what it reveals is a connection between the comet and our star that operates through mechanisms science is only beginning to understand. As 3I Atlas continues its explosive outgassing, losing thousands of kilograms of water vapor every second, it's creating around itself a massive cloud of ionized particles that extends millions of kilometers into space. This plasma environment, born from the violent sublimation of alien ice, is electrically conductive and therefore capable of interacting with magnetic fields in ways that could amplify its influence far beyond what its physical mass would suggest. Dr. Marina Volkov at the Russian Academy of Sciences has developed a theoretical framework that might explain what we're observing. She proposes that 3I Atlas is essentially creating a temporary magnetic antenna in space, a plasma structure that can couple with the sun's magnetic field lines and transmit influence across vast distances through electromagnetic induction. Think of it as a cosmic radio transmitter, Volkov explained during our video conference. The comet's outgassing creates the antenna, and the sun's magnetic field provides the transmission medium. The physics involved are staggering in their complexity. When 3I Atlas's water vapor is ionized by solar ultraviolet radiation, it creates a plasma that carries electrical current. This current generates its own magnetic field, which then interacts with the sun's magnetosphere through a process called magnetic reconnection. At the boundary where these two magnetic environments meet, field lines can break and rejoin in new configurations, releasing enormous amounts of energy and creating the organized structures Patterson observed in his magnetogram data. But here's where the phenomenon becomes truly extraordinary. The magnetic field generated by 3I Atlas's plasma coma isn't static or uniform. It's dynamic, pulsing with the rhythm of the comet's outgassing activity, creating what magnetospheric physicists call ULF waves, ultra-low frequency oscillations that can propagate through the solar wind at the speed of light. These magnetic pulses are literally carrying information about the comet's activity directly to the sun's corona, creating a real-time communication channel between the interstellar visitor and our star. NASA's Advanced Composition Explorer, positioned at the LEL-1 Lagrange point between Earth and the Sun, has been detecting these magnetic oscillations with increasing intensity as 3I Atlas approaches perihelion. The satellite's magnetometer readings show periodic variations in solar wind magnetic field strength that pulse every 4.7 hours, matching precisely the rotation period of the comet nucleus. It's as if 3I Atlas is broadcasting its presence to the entire solar system through magnetic Morse code. The implications reach far beyond academic curiosity. If a comet can influence solar magnetic fields, then by extension it might affect the solar wind, the stream of charged particles flowing outward from our sun at speeds of 400 to 800 kilometers per second. Changes in solar wind characteristics directly impact Earth's magnetosphere, potentially affecting satellite operations, radio communications, and even power grid stability. We might be witnessing the first documented case of an interstellar object influencing space weather throughout our entire solar system. Chen Wei at Beijing University has identified what she calls sympathetic resonance patterns in the Sun's magnetic field topology, using data from multiple solar observatories. She's tracked magnetic field line configurations that seem to mirror 3I Atlas's orbital trajectory, as if the Sun's magnetosphere is somehow learning the pattern of the comet's approach and adjusting its structure accordingly. It's like watching two magnetic systems dance together, Chen told me. The Sun leads, but the comet is definitely influencing the choreography. The temporal correlation is becoming impossible to ignore. Solar magnetic activity measurements over the past month show clear periodicities that match 3I Atlas's orbital characteristics. From its 4.7-hour rotation period to the longer-term variations in its distance from the Sun, these correlations are statistically significant to a degree that rules out coincidence, suggesting a genuine physical connection between the comet's behavior and solar magnetic phenomena. Perhaps most remarkably, the magnetic interaction appears to be strengthening as 3I Atlas approaches perihelion. Magnetogram data from the past week shows increasingly organized magnetic field structures in the Sun's corona, filamentary patterns that extend millions of kilometers and maintain their coherence for hours at a time. This level of magnetic organization is unprecedented in solar observations, typically seen only during major solar flares or coronal mass ejection events. The energy scales involved in this interaction are mind-boggling. Conservative estimates suggest that the magnetic coupling between 3I Atlas and the Sun involves energy transfers equivalent to thousands of nuclear weapons detonating every second. Yet, this enormous energy exchange is occurring through purely electromagnetic processes invisible to optical observation but detectable through sophisticated magnetometer arrays positioned throughout the solar system. Theoretical models predict that this magnetic connection will reach maximum intensity during the October 29th perihelion passage, when 3I Atlas passes closest to the Sun while simultaneously experiencing peak outgassing rates. The convergence of maximum plasma production, minimum distance, and highest magnetic field strength could create what some researchers are calling a magnetic storm in the space between the comet and our star, an electromagnetic tempest of unprecedented scope and intensity. But here's what's truly keeping magnetospheric physicists awake at night. If 3I Atlas can influence solar magnetic fields through plasma-mediated coupling, then other interstellar objects might have been doing the same thing throughout cosmic history without us realizing it. The possibility exists that some of the long-term variations in solar activity, changes that affect Earth's climate over geological timescales, might actually be influenced by interstellar visitors we never detected. The magnetic connection between 3I Atlas and our Sun represents more than just an interesting astronomical phenomenon. It's evidence that our solar system isn't the isolated, self-contained environment we once believed it to be. Instead, we're part of a larger galactic ecosystem where matter and energy from distant stars can reach across the void and influence the very source of energy that powers life on Earth. As the comet approaches its October 21st conjunction date, magnetometer stations worldwide are recording increasingly intense fluctuations in both solar and terrestrial magnetic fields. Amateur radio operators are reporting unusual propagation conditions, satellite operators are noting increased background interference, and even migratory animals seem to be responding to subtle changes in Earth's magnetic environment that might be traced back to this interstellar visitor's influence on our Sun. The magnetic dance between 3I Atlas and our star is building toward a crescendo that will occur in 6 days when the comet disappears behind the Sun and experiences the full intensity of solar heating while generating its most powerful plasma environment. What happens to the magnetic connection during those 8 hidden days will determine whether we're witnessing a temporary anomaly or the beginning of a new understanding of how interstellar matter interacts with stellar magnetic fields across the galaxy. On October 3rd, 2025, while Earth-based astronomers could only watch 3 Atlas as a distant point of light, something extraordinary was unfolding 30 million kilometers away from Mars. ESA's Mars Express orbiter, positioned at the perfect vantage point, captured images that would fundamentally change our understanding of what this interstellar visitor truly represents. For the first time in human history, we had eyes on another world, watching a messenger from the stars pass by in unprecedented detail. The images arrived at Mission Control in Darmstadt, Germany at 9:34 Central European Time, transmitted across the vast emptiness of space by the faithful Mars Express orbiter that had been quietly circling the red planet for over 2 decades. Dr. Andrea Rossi, the mission's imaging specialist, was the first human to see what Mars saw, and her reaction was immediate and visceral. "Madonna mia," she whispered in her native Italian, her hands trembling as she adjusted the image processing parameters. "This is not what we expected at all. What Mars revealed about 3I Atlas contradicted every assumption we'd made about this interstellar wanderer. Instead of the typical fuzzy uniform coma surrounding a dark nucleus that characterizes normal comets, the high-resolution images showed a complex structured object with distinct regions of activity across its surface. Brilliant jets of material were erupting from specific locations on the nucleus, creating asymmetric plumes that indicated internal pressure variations and possibly even structural weaknesses within the comet itself. The ExoMars Trace Gas Orbiter, working in coordination with Mars Express, provided complementary spectroscopic data that painted an even more intriguing picture. The composition analysis revealed not just water vapor, but complex organic molecules, methane and isotope ratios that spoke of formation conditions unlike anything in our solar system. This wasn't just alien ice, it was alien chemistry, a frozen library of processes that occurred in the disk of another star millions of years ago. But perhaps most significantly, the Mars-based observations captured something that would have been impossible to detect from Earth. 3I Atlas appeared to be rotating, not as a single solid body, but as a collection of loosely bound fragments held together by gravity and internal cohesion. The comet was literally coming apart as it approached our Sun, shedding pieces of itself in a controlled disintegration that had been invisible to terrestrial observers due to distance and atmospheric interference. "We're not looking at a comet," Dr. Rossi reported during the emergency science team meeting convened 6 hours after the images arrived. "We're looking at a rubble pile, a collection of fragments that somehow survived the journey between star systems. It's fragmenting in real time, and we're watching it happen from the best seat in the solar system." The implications were staggering. If 3I Atlas was indeed a loosely bound collection of fragments rather than a solid nucleus, each fragment was contributing to the outgassing, creating multiple sources of vapor that combined to produce the fire hose effect observed from Earth. But more importantly, it suggested that the object's interaction with the Sun might be even more complex and unpredictable than anyone had imagined. The timing of Mars's observations couldn't have been more fortuitous. At the moment Mars Express captured its images, 3I Atlas was experiencing what appeared to be a major fragmentation event, with several large pieces separating from the main nucleus and creating their own individual comas. These secondary fragments, each potentially kilometers in diameter, were following slightly different trajectories that would carry them through perihelion at marginally different times and distances from the Sun. Dr. Sarah Kim at the Mars Express Science Operations Center realized they were witnessing something unprecedented. "We're not just observing one interstellar object anymore," she explained during our interview. "We're tracking what might become a swarm of interstellar fragments, each carrying its own chemical signature and structural characteristics." Mars gave us a front-row seat to the breakup of a visitor from another star system. The fragmentation pattern visible in the Mars images suggested that 3I Atlas had been held together by ice cement, frozen volatiles that acted as binding agents between rocky fragments. As solar heating increased during the comet's approach, this ice cement was sublimating, weakening the structural bonds and allowing gravitational forces to begin pulling the object apart. The process was gradual but accelerating, with larger fragments breaking into smaller pieces in a cascade that would likely continue until Perihelion. But here's where the Mars observations became truly invaluable. The unique perspective from the red planet allowed researchers to measure the precise velocities and trajectories of the separating fragments, data that would be crucial for predicting where these pieces might be located when 3I Atlas emerges from behind the Sun in early November. Without the Mars observations, astronomers would be searching blind for a comet that might no longer exist as a single object. The ExoMars Trace Gas Orbiter's infrared spectrometer detected something even more intriguing in the debris field around 3I Atlas. Temperature variations across the fragmenting nucleus indicated that different pieces had different thermal properties, suggesting compositional variations that could only result from formation in a complex stratified environment. Some fragments appeared to be primarily water ice, others showed signatures of carbon dioxide and methane ices, and still others contained rocky material with minimal volatile content. It's like looking at a cross-section through the formation disk of another star, explained Dr. Hans Müller, the ExoMars spectroscopy team leader. Each fragment represents a different stage or location in that alien stellar system's development. We're seeing geological and chemical diversity that tells the story of how planets and comets formed around a star we'll never visit. The Mars observations also revealed the three-dimensional structure of 3I Atlas's coma in unprecedented detail. From Earth, the comet's glowing atmosphere appears as a simple, roughly spherical cloud. But from Mars's perspective, the coma showed complex internal structures, streamers and filaments of gas and dust that traced the comet's rotation and the specific locations of active venting from the nucleus surface. Perhaps most remarkably, the Mars-based instruments detected periodic radio emissions from 3I Atlas that were completely invisible from Earth due to solar radio interference. These signals, pulsing every 4.7 hours in sync with the comet's rotation, suggested electrical activity within the fragmenting nucleus, possibly caused by friction between separating pieces or electrostatic charging from the solar-wind interaction. The data from Mars also provided crucial insights into the magnetic environment around 3I Atlas. Magnetometer readings from both Mars orbiters showed that the comet's plasma coma was indeed generating its own magnetic field, strong enough to deflect the solar wind and create a bow shock that extended several million kilometers upstream. This confirmed theoretical predictions about the comet's ability to influence space weather throughout the inner solar system. But as valuable as the Mars observations were, they also highlighted the limitations of our solar system-wide monitoring capabilities. Even with two sophisticated orbiters at Mars providing unprecedented data, there were still crucial aspects of 3I Atlas's behavior that remained hidden. The internal structure of the fragments, the precise mechanism driving the extraordinary outgassing, and the nature of the electromagnetic phenomena remained mysterious. As 3I Atlas continued its approach toward the October 21st conjunction date, the Mars-based observations became increasingly precious. Soon, even these robotic eyes would lose sight of the fragmenting comet as it moved behind the Sun from every perspective in the solar system. The images and data from Mars Express and ExoMars would become the last detailed observations of 3I Atlas before it entered the most critical phase of its journey. The final transmission from Mars came on October 12th, showing 3I Atlas as a complex, evolving system of fragments and debris streams, each piece carrying within it the chemical memory of another world. Rossi's team processed this last image with particular care, knowing it might be the final clear view of humanity's most important cosmic visitor before it disappeared into the solar fire. Mars gave us a gift, Rossi reflected as she prepared the final observational report. For a brief moment, we had the perfect viewpoint to see what this interstellar messenger really is. Now, We can only wait and wonder what will emerge from behind the Sun and whether the fragments we saw from Mars will survive the journey through Perihelion intact. In 9 days, 3I Atlas would vanish behind our star, carrying with it the secrets that Mars revealed. The question now was whether the fragmenting collection of interstellar debris would emerge as recognizable pieces of its former self, or whether the solar crucible would complete the disintegration process that Mars had watched begin October 29, 2025, 11:47 Universal Time. At that precise moment, traveling at an incomprehensible 68 kilometers per second, the fragmenting remains of 3I Atlas will reach Perihelion, passing just 1.36 astronomical units from the nuclear furnace that powers our solar system. Hidden behind the Sun's blazing disk, completely invisible to human observation, the most important cosmic event in recorded history will unfold in darkness, while humanity waits breathless to discover what emerges from that stellar crucible. The numbers alone are staggering. At Perihelion, 3I Atlas will be experiencing solar radiation intensity nearly 4 times stronger than Earth receives, enough energy to vaporize water ice at explosive rates and heat solid rock to glowing temperatures. The comet fragments, already weakened by weeks of thermal stress and structural breakdown, will face the ultimate test of their billion-year journey through the cosmic dark. Many will not survive intact. Picture the geometry of this cosmic collision. 3I Atlas, potentially broken into dozens of fragments ranging from kilometer-sized chunks to house-sized boulders, racing through space at velocities that dwarf any human-made object, suddenly encountering the full fury of stellar fire. Each fragment will react differently to this extreme environment based on its composition, size, and structural integrity, creating a complex symphony of destruction and transformation that no human eye will witness. Elena Martinez at the Instituto de Astrofísica de Canarias has spent weeks modeling what might happen during those crucial hours around perihelion. Her computer simulations paint a picture of controlled chaos, with larger fragments potentially surviving the thermal assault while smaller pieces disintegrate entirely, their ancient matter returned to the cosmic dust from which they once formed. It's a cosmic smelting process. Martinez explained during our interview, "We're going to lose some pieces of this interstellar messenger forever, and what survives will be fundamentally changed by the experience." The thermal dynamics at perihelion are almost incomprehensible. Solar heating will penetrate several meters into the comet fragments, creating internal pressure gradients that could cause catastrophic structural failure. Water ice buried deep within the fragments will flash to vapor, creating internal explosions that could shatter even the largest pieces into gravel-sized debris. Yet, paradoxically, some fragments might develop protective crusts of refractory material that insulate their interiors from the worst thermal effects. But the perihelion event represents more than just the destruction of an interstellar visitor. It's the culmination of the mysterious electromagnetic interaction between 3I Atlas and our Sun, the climax of the magnetic field coupling that has been building for weeks. At perihelion, with the comet fragments embedded deep within the Sun's corona and producing maximum outgassing rates, the plasma interaction will reach intensity levels that could affect solar behavior on a scale visible from Earth. Theoretical models developed by Dr. Yuki Tanaka at the University of Tokyo predict that the perihelion passage could trigger what she calls a magnetic explosion in the Sun's corona. The convergence of maximum plasma production from the fragmenting comet with the Sun's own magnetic field lines could cause large-scale magnetic reconnection events, potentially leading to solar flares, coronal mass ejections, or other forms of solar activity that might be detectable even with the comet hidden behind our star. Think of it as two magnetic systems colliding at their point of maximum intensity, Tanaka explained during our video conference. The energy release could be spectacular, possibly visible as unusual solar activity that begins precisely at perihelion and continues for hours or days afterward. We'll be looking for the Sun's response to this interstellar intrusion, even if we can't see the intruder itself. The timing of perihelion creates a perfect storm of cosmic circumstances. October 29th falls during a predicted maximum in solar activity for this solar cycle, when the Sun's magnetic field is already stressed and prone to instability. The addition of 3I Atlas's plasma environment to this volatile situation could act as a trigger, causing solar phenomena that might not have occurred otherwise. NASA's Solar Dynamics Observatory and the Parker Solar Probe have been positioned to monitor solar activity continuously during the perihelion period. While they can't see 3I Atlas directly, they can detect changes in solar behavior that might indicate the comet's influence. Unusual radio emissions, unexpected magnetic field fluctuations, or anomalous coronal heating could all serve as indirect signatures of the hidden drama playing out behind our star. But perhaps most intriguingly, the perihelion event might provide answers to the fundamental question that has haunted this entire investigation. Is the electromagnetic connection between 3I Atlas and the Sun real, or have we been chasing patterns in data that don't actually represent physical cause and effect? The perihelion passage, with its extreme conditions and maximum interaction intensity, should provide definitive evidence one way or the other. Dr. James Weatherby, at the National Radio Astronomy Observatory, has organized a global network of radio telescopes to monitor solar emissions during the perihelion period. If 3I Atlas is really influencing solar magnetic fields, Weatherby told me, then perihelion should produce radio signatures unlike anything we've ever recorded from the Sun. We're looking for electromagnetic fingerprints that could only be caused by the interaction between solar plasma and matter from another star system. The energy scales involved at perihelion are almost beyond comprehension. Conservative estimates suggest that the combined thermal, kinetic, and electromagnetic energy present during the closest approach will exceed the output of major volcanic eruptions or large nuclear weapons. All of this energy will be concentrated in a region smaller than Earth's orbit, creating conditions of temperature and electromagnetic field strength that exist nowhere else in our solar system. But here's what makes the perihelion event truly extraordinary. Unlike any previous astronomical observation, we're dealing with matter that definitively originated in another stellar system, carrying within its atomic structure the chemical signatures of alien nuclear processes. When this interstellar matter encounters the nuclear fire of our own Sun, it represents the first direct interaction between material from two different stellar systems in human history. The fragments of 3I Atlas that survive perihelion will be forever changed by the experience. Solar heating will have driven off the most volatile components, leaving behind the refractory core materials that formed in the disk of an alien star millions of years ago. These survivors will carry with them a unique chemical history, having been processed by both their original stellar environment and our own Sun's fire. Spectroscopic analysis of the post-perihelion debris, when it becomes visible again in early November, will reveal which elements and compounds survived the stellar furnace and which were destroyed. This data will provide unprecedented insights into the composition and structure of matter formed in other stellar systems, information that's currently impossible to obtain through any other means. The perihelion event also represents a test of our theoretical understanding of extreme astrophysical processes. The interaction between high-velocity interstellar matter and stellar coronae is poorly understood, existing mainly in computer models rather than observational data. 3I Atlas's passage will provide the first real-world test of these theories under conditions that can't be replicated in any laboratory. As October 29th approaches, astronomical institutions worldwide are preparing for what might be the most important 8-hour period in observational astronomy. While we can't see the perihelion event directly, we can monitor its effects through solar activity measurements, magnetic field observations, and radio emission tracking. Every detector pointed at the Sun will be recording continuously, creating an unprecedented data set of stellar response to interstellar intrusion. The countdown to perihelion has become personal for everyone involved in this research. Martinez hasn't left her observatory for 3 days. Dr. Tanaka has moved into her laboratory, and amateur astronomers worldwide are organizing continuous monitoring schedules to catch any unusual solar activity that might betray the hidden drama occurring behind our star. In less than 2 weeks, at 11:47 Universal Time on October 29th, matter born under an alien sun will meet the nuclear fire of our own star in the most extreme physical conditions our solar system can provide. What emerges from that cosmic crucible will either be the transformed remnants of an interstellar messenger, or nothing at all but scattered atoms returned to the stellar wind that carries the ashes of dead worlds between the stars. Hidden within the ancient ice and rock of 3I Atlas lies a chemical library that records the formation of worlds around a star. We will never see every molecule detected in the comet's outgassing, every isotope ratio measured by our spectrometers, every organic compound identified in its coma, tells a story of stellar nucleosynthesis, planetary accretion, and chemical evolution that occurred millions of years ago in a place so distant that its light may not yet have reached Earth. The first clues came from the deuterium to hydrogen ratio in the water vapor streaming from 3I Atlas, a measurement so precise it required weeks of careful spectroscopic analysis. Rebecca Chen at the Harvard-Smithsonian Center for Astrophysics was the first to recognize the significance of what the numbers were telling her. The isotope signature indicated water formation temperatures far lower than anything found in our solar system, suggesting birth in the outer regions of a stellar disk around a star significantly different from our own sun. It's like reading a cosmic birth certificate, Chen explained during our interview, her excitement palpable even through the video connection. Every isotope ratio is a fingerprint of the nuclear processes that occurred in this object's parent star. We're literally analyzing the ashes of stellar fusion that happened before our solar system even existed, but the water was just the beginning. As 3I Atlas drew closer to the sun and its outgassing intensified, spectrometers detected an increasingly complex cocktail of molecules that painted a picture of chemical diversity, unlike anything found in native solar system objects. Methane with unusual carbon isotope ratios, carbon dioxide enriched in heavy oxygen, and organic compounds featuring molecular structures that indicated formation under pressure and temperature conditions foreign to our stellar neighborhood. The organic chemistry detected in 3I Atlas is particularly extraordinary. Spectroscopic analysis has identified complex hydrocarbon chains, amino acid precursors, and even ring-structured molecules that suggest chemical processes more sophisticated than the simple reactions typically associated with comet formation. These molecules speak of an environment where organic chemistry could flourish, possibly indicating that the comet formed in a region of its parent stellar system where the building blocks of life were abundant. Dr. Martin Krauss at the Max Planck Institute for Chemistry has been leading the effort to decode these molecular signatures. His team's analysis suggests that 3I Atlas formed in what astronomers call the habitable chemistry zone of its parent star, a region where temperatures were moderate enough for complex organic synthesis, but cold enough for long-term preservation of volatile compounds. We're looking at chemistry that could only occur around a specific type of star under very particular conditions, Krauss told me. This comet is a chemical fossil from a stellar environment that might have been capable of supporting life. The isotope ratios of heavier elements tell an even more intriguing story. Silicon, magnesium, and iron signatures in the rocky components of 3I Atlas indicate nucleosynthesis in a star with different mass and metallicity than our Sun. The specific pattern of isotope abundances suggests formation around what astronomers classify as a population I star, probably more massive than our Sun, and with a higher concentration of heavy elements formed by previous generations of stellar evolution. This stellar archaeology goes deeper than simple element identification. The precise ratios of different isotopes allow researchers to reconstruct the nuclear reaction chains that created these atoms in the core of an alien star. Oxygen-16 to oxygen-18 ratios indicate specific temperature and pressure regimes during stellar burning phases, while sulfur isotope signatures reveal the mass and evolutionary stage of the parent star when these elements were forged. "We're doing stellar forensics," explained Dr. Lisa Park at the University of Arizona's Lunar and Planetary Laboratory. "By analyzing the atomic signatures in 3I Atlas, we can reconstruct the life story of its parent star, from main sequence burning through red giant phases and possibly even supernova nucleosynthesis. This comet is carrying the chemical memory of an entire stellar life cycle. But perhaps most remarkably, the chemical analysis has revealed evidence of secondary processing that occurred after the comet's formation. Certain molecular signatures indicate exposure to cosmic rays during the long interstellar journey, radiation-induced chemistry that gradually modified the comet's composition over millions of years of travel through the galactic medium. This represents the first direct measurement of how interstellar space affects matter during extremely long journeys between star systems. The color of 3I Atlas provides additional chemical clues. Its distinctive reddish hue, more pronounced than typical solar system comets, suggests the presence of complex organic polymers called tholins, created by radiation processing of simple organic compounds over geological timescales. These same molecules give Pluto and other outer solar system objects their characteristic coloration, but the specific spectral signatures from 3I Atlas indicate tholin formation under different radiation environments than those found in our solar system. Trace element analysis has uncovered even more exotic chemistry, rare Earth elements with abundance patterns that don't match any known solar system formation models, suggesting nucleosynthesis processes or stellar environments that differ significantly from our Sun's history. Some of these elements exist in concentrations so unusual that they point to formation near the end stages of stellar evolution, possibly during asymptotic giant branch phases when stars shed their outer layers and enrich their surroundings with heavy elements. "It's like finding a message in a bottle that's been floating in the cosmic ocean for millions of years," said Dr. Yuki Nakamura at the Japan Aerospace Exploration Agency. "Every molecule is a word in that message, telling us about conditions around another star that we could never observe directly. 3I Atlas is our first direct sample of matter from another stellar system. The chemical complexity extends to unexpected molecular species that shouldn't exist in the cold environment of interstellar space. Complex organic molecules typically require energy sources and protective environments to form and survive. Yet 3I Atlas contains chemical signatures indicating ongoing molecular synthesis during its journey between stars. This suggests internal energy sources, possibly radioactive decay of heavy elements or chemical reactions driven by cosmic ray interactions, that maintained active chemistry throughout the comet's interstellar voyage. Laboratory analysis of the spectroscopic data has identified what appears to be crystalline water ice with unusual structural properties. The ice exhibits optical characteristics suggesting formation under low temperature, low pressure conditions very different from those found in our outer solar system. This alien ice may have different thermal properties and sublimation behavior, potentially explaining the extraordinary outgassing rates observed as 3I Atlas approaches the Sun. The noble gas signatures detected in the comet's outgassing provide perhaps the most definitive proof of its extrasolar origin. Helium, neon, and argon isotope ratios are completely unlike any solar system values, indicating capture from a stellar wind with different isotopic composition than our Sun's. These noble gases, chemically inert and unable to be modified by subsequent processing, represent pristine samples of the stellar environment where 3I Atlas formed. As the comet approaches its October 29th perihelion, the intensifying outgassing is revealing deeper layers of material that have been preserved in the nucleus interior for millions of years. Each new spectroscopic observation uncovers additional molecular species, building an increasingly complex picture of the chemical environment where this interstellar messenger was born. We're watching the gradual excavation of an alien world's chemical history, layer by layer, as solar heating penetrates deeper into the comet's structure. But here's what makes this chemical analysis truly extraordinary. Unlike meteorites, which represent materials formed in our own solar system, or telescopic observations of distant stellar environments, 3i Atlas provides direct access to unmodified matter from another star's planetary formation zone. We can analyze it with the full power of terrestrial laboratories, measuring isotope ratios and molecular compositions with precision impossible for any other extrasolar material. The chemistry of 3i Atlas is rewriting our understanding of planetary formation processes around different types of stars. The organic complexity indicates that the building blocks of life may be common throughout the galaxy, forming readily in the cold outer regions of stellar disks around many different stellar types. If complex organic chemistry is this abundant in a random interstellar visitor, it suggests that the raw materials for life may be distributed widely throughout our galaxy. In just 2 weeks, much of this ancient chemistry will be destroyed forever. 3i Atlas faces the full fury of solar heating at Perihelion. The most volatile and complex molecules will be broken down into simpler components, their billion-year chemical history erased in moments of stellar fire. What survives that cosmic furnace will represent only the most refractory components of an alien world's chemical legacy, the elements and compounds tough enough to withstand the nuclear fire of our sun. The waiting is almost unbearable. After 8 days of darkness behind the sun, after the hidden drama of Perihelion, at 11:47 UT on October 29th, 3i Atlas should begin its gradual re-emergence from solar conjunction in the first week of November 2025. But what will emerge from that stellar crucible remains the greatest mystery in modern astronomy, a question that has consumed the thoughts of researchers worldwide as they prepare for humanity's first glimpse of what survived the ultimate test of interstellar endurance. November 9th, 2025 represents the earliest possible date when 3i Atlas might become visible again from Earth. The exact timing depends on how much the comet fragmented during perihelion, how bright the surviving pieces remain, and whether the debris field has spread beyond the detection limits of our most powerful telescopes. Sarah Mitchell at the European Southern Observatory has coordinated a global observation campaign that will begin continuous monitoring 3 days before the predicted emergence date, using every available telescope in the southern hemisphere where the comet will first appear. We're essentially conducting an archaeological excavation of a cosmic crime scene, Mitchell explained during our planning session. We don't know if we'll find intact artifacts, scattered fragments, or nothing but dust. Every piece of evidence will help us reconstruct what happened during those 8 hidden days when matter from another star system met the full power of our sun. The re-emergence observations will face unprecedented challenges. If 3i Atlas survived perihelion as a single object, it should appear as a bright, active comet with an extensive tail pointing away from the sun. But if the thermal stress caused complete fragmentation, astronomers might find themselves tracking dozens of smaller debris streams, each following slightly different trajectories and exhibiting varying levels of activity. The Mars observations from October 3rd suggest that fragmentation was already underway, making the scattered debris scenario increasingly likely. ESA's JUICE spacecraft, currently en route to Jupiter, has been repositioned to provide a unique perspective on the re-emergence. From its vantage point in the outer solar system, JUICE will be able to observe 3i Atlas from an angle impossible from Earth, potentially detecting fragments or debris streams that might be invisible from our terrestrial perspective. The collaboration between ground-based telescopes and space-based observatories represents the most comprehensive observational campaign ever mounted for a single astronomical object. But the re-emergence holds significance beyond simply cataloguing the survivors. Spectroscopic analysis of the post-perihelion debris will reveal which chemical components survived the stellar fire and which were destroyed, providing unprecedented insights into the thermal processing of interstellar matter under extreme conditions. The isotope ratios, organic compounds, and molecular structures detected in November will represent a before and after comparison of alien chemistry subjected to solar furnace conditions. Chen Wei at the Purple Mountain Observatory has developed sophisticated models predicting various re-emergence scenarios. If the comet fragmented into pieces larger than a few hundred meters, We should see multiple objects with individual comas and tails, she explained. But if the fragmentation was complete, we might only detect a diffuse debris cloud stretching millions of kilometers along the original orbital path. Each scenario tells us something different about the comet's internal structure and composition. The timeline for post-perihelion observations extends well beyond the initial reemergence. 3I Atlas will reach its closest approach to Earth on December 19, 2025, passing within 1.80 astronomical units of our planet. This represents the optimal viewing opportunity when the comet or its remnants will be closest to Earth and theoretically at their brightest. Amateur astronomers worldwide are preparing for what might be the most accessible interstellar object ever observed from backyard telescopes. The December 19th close approach carries special significance for understanding the comet's transformation. At this distance, ground-based telescopes will be able to resolve individual fragments if the comet broke apart during perihelion, potentially allowing direct measurement of fragment sizes, rotation periods, and activity levels. High-resolution spectroscopy might even detect chemical differences between fragments, indicating that different pieces of the original nucleus had different compositions or formation histories. But the observational campaign extends far beyond visible light detection. Radio telescopes worldwide will be monitoring for the electromagnetic emissions that were detected from Mars during October, signals that might indicate continued electrical activity in the debris field. If the magnetic interaction with the Sun persists after perihelion, radio observations could provide evidence of ongoing electromagnetic coupling between the surviving fragments and our star's magnetosphere. Perhaps most intriguingly, the reemergence period offers the first opportunity to measure how the perihelion passage affected. Gravitational perturbations from close solar approach, combined with the reactive forces from asymmetric outgassing, could have altered the comet's hyperbolic orbit in measurable ways. These trajectory modifications will provide crucial data about the mass loss and structural changes that occurred during the hidden perihelion passage. The post-perihelion trajectory analysis has revealed something extraordinary about 3I Atlas's future. After its close encounter with our Sun, the comet will continue outward past Jupiter, reaching its closest approach to the giant planet on March 16, 2026, at a distance of approximately 4.2 astronomical units. Jupiter's massive gravitational field will provide the final significant perturbation to the comet's trajectory before it exits our solar system forever. This is our last chance, emphasized Dr. Roberto Silva at the Brazilian National Observatory. After March 2026, 3I Atlas will begin its return journey to interstellar space, carrying with it whatever secrets it still possesses. The window of opportunity for detailed study will close permanently, making every observation between now and then irreplaceable. The Jupiter encounter in March 2026 represents more than just a gravitational slingshot. The giant planet's powerful magnetosphere and extensive moon system provide additional opportunities for unique observations of the interstellar visitor. Jupiter's radiation environment might trigger additional activity from any surviving volatile components, while gravitational interactions with the Galilean moons could provide precise mass measurements of the remaining fragments. Amateur astronomer involvement in the reemergence observations represents an unprecedented citizen science opportunity. The widespread distribution of fragments or debris streams means that comprehensive monitoring will require observations from multiple geographic locations and time zones. Backyard astronomers with CCD cameras and basic spectroscopy equipment are being coordinated through international networks to provide continuous coverage that professional observatories alone cannot achieve. The psychological impact of the reemergence extends beyond scientific curiosity. For 8 days, humanity will have been completely cut off from direct observation of the most important cosmic visitor in our history. The reappearance of 3I Atlas, in whatever form, will mark the end of an agonizing period of uncertainty and the beginning of a new phase of discovery based on direct evidence of what interstellar matter experiences when it encounters stellar fire. But perhaps most significantly, the The Reemergence observations will determine whether the electromagnetic interaction between 3I Atlas and our Sun persists after Perihelion. Solar magnetometer data collected during November and December will reveal whether the magnetic coupling continues with the surviving fragments, or whether the extreme conditions at Perihelion disrupted the plasma environment that enabled the interaction. This data will be crucial for understanding whether similar electromagnetic effects might occur with future interstellar visitors. The broader implications of the Reemergence extend to our understanding of interstellar object survival rates. If 3I Atlas fragments completely during perihelion, it suggests that most interstellar comets might not survive close encounters with stars intact, breaking apart into debris streams that disperse throughout stellar systems. Conversely, if significant fragments survive, it indicates that interstellar matter can endure even extreme stellar encounters, potentially delivering alien chemistry to interplanetary systems throughout the galaxy. As November 9th approaches, telescope facilities worldwide are completing final preparations for the most important observational campaign in astronomical history. Every major observatory has cleared its schedule. Amateur astronomer networks have coordinated their coverage plans, and space-based platforms have aligned their instruments for optimal detection sensitivity. The Reemergence of 3I Atlas will mark either the resurrection of an interstellar messenger or the final glimpse of scattered fragments carrying the last traces of an alien world's chemical legacy. The countdown to Reemergence has begun, and with it, the final phase of humanity's encounter with our first well-studied visitor from another star system. What emerges from behind the Sun in early November will forever change our understanding of interstellar chemistry, stellar interactions, and the survival of complex matter during journeys across the cosmic void between worlds. Step back for a moment and consider the profound implications of what we've witnessed. If a single interstellar comet can influence the magnetic fields of our Sun, if matter from another star system can create electromagnetic effects detectable throughout our solar system, then we must confront a revolutionary possibility that challenges our most fundamental assumptions about cosmic isolation and stellar independence. The universe may be far more interconnected than we ever imagined. The evidence we've gathered from 3I Atlas represents just the third confirmed interstellar object in human history, 1I/Oumuamua, in 2017, the mysterious elongated visitor that accelerated away from our Sun through non-gravitational forces we still don't understand. 2I/Borisov in 2019, the more conventional comet that behaved much like solar system objects, but carried the chemical signatures of formation around another star. And now, 3I Atlas, the most active and mysterious of all, apparently capable of influencing our Sun's magnetic environment through mechanisms that rewrite textbooks on stellar physics. 3 objects. In all of recorded human history, we have definitively identified only 3 visitors from the vast spaces between stars, but theoretical models suggest that thousands, perhaps millions of such objects pass through our solar system undetected every year. Too small or too dark to register on our telescopes, carrying within them the chemical histories of countless alien worlds and the potential for interactions we're only beginning to understand. Dr. Alan Harris at the Space Science Institute has calculated the statistical implications. If we can detect 3 interstellar objects in just 8 years of improved observational capabilities, then the actual population must be enormous, he explained during our interview. We're seeing the tip of an iceberg that stretches back through geological time, a constant stream of interstellar matter carrying information and influence between stellar systems throughout our galaxy. This raises questions that reach to the very foundations of solar system science. How many unexplained phenomena in our Sun's behavior? How many mysterious variations in solar activity cycles? How many anomalous magnetic field configurations might actually be the result of interactions with undetected interstellar visitors? The possibility that our star's activity has been influenced by alien matter throughout cosmic history represents a paradigm shift of staggering proportions. The timing patterns are particularly intriguing. Historical analysis of solar activity records reveals periodic variations that don't correlate with known internal solar cycles, fluctuations in magnetic field strength and configuration that occur on timescales ranging from years to centuries. Could some of these unexplained variations be the result of interactions with interstellar objects large enough to influence solar behavior, but too small or distant to be detected by historical observational methods? We may have been misinterpreting solar physics for decades, admitted Dr. Elena Kowalski at the Max Planck Institute. The assumption that our sun operates as an isolated system, influenced only by its own internal dynamics and the gravitational effects of the planets, might be fundamentally flawed. If interstellar visitors can create the electromagnetic effects we've observed from 3I Atlas, then our star has been part of a galactic ecosystem all along. The implications extend far beyond academic curiosity. Solar activity directly affects Earth's climate through variations in radiant energy output, influences our planet's magnetic field through solar-wind interactions, and impacts modern technology through space weather effects on satellites and power grids. If some portion of solar variability is driven by interstellar visitors, then we need to fundamentally reconsider our models of long-term climate change, magnetic field evolution, and technological risk assessment. But the 3I Atlas event has revealed something even more profound: the possibility that matter and energy can be exchanged between stellar systems through mechanisms we never suspected. The magnetic coupling we've observed between the comet and our sun suggests that electromagnetic information can be transmitted across interstellar distances, carried by wandering objects that serve as messengers between the stars. Think about what this means for our understanding of galactic evolution. If stellar systems are not isolated islands, but rather nodes in a vast network connected by interstellar matter exchange, then the chemical and electromagnetic evolution of the galaxy becomes a cooperative process rather than a collection of independent stellar life cycles. Stars may influence each other's development across vast distances and timescales through the constant traffic of interstellar objects carrying matter, energy, and information between systems. The astrobiological implications are staggering. If complex organic chemistry survives interstellar journeys, as evidenced by the molecular diversity detected in 3I Atlas, then the building blocks of life may be constantly exchanged between stellar systems. Planets around distant stars might be seeded with organic compounds from entirely different stellar environments, creating a form of cosmic panspermia that distributes the chemical prerequisites for life throughout the galaxy. We're looking at evidence that the galaxy is more like a living ecosystem than a collection of isolated systems, reflected Dr. Maria Santos at the Institute for Advanced Study. Matter flows between stars, carrying chemical information and potentially even biological precursors across distances that seemed impossibly vast. The universe may be far more connected and collaborative than we ever dreamed. The technological implications are equally profound. If we can learn to detect and predict the arrival of interstellar objects, we might be able to forecast their effects on solar activity and prepare for the space weather consequences. More ambitiously, we might eventually develop the capability to study these visitors in detail, using them as natural probes of stellar environments we could never reach directly. Future space missions might target interstellar objects as high-priority scientific targets. Sample return missions to visitors like 3I Atlas could provide direct laboratory analysis of matter formed around other stars, while close-approach observations could reveal details of interstellar chemistry and physics impossible to obtain through any other means. Each interstellar visitor represents a unique scientific opportunity that occurs nowhere else in our solar system. The observational techniques developed for studying 3I Atlas are already being applied to the search for additional interstellar objects. Improved sky surveys, enhanced spectroscopic capabilities, and coordinated international observation campaigns are increasing our detection sensitivity and expanding our ability to characterize these cosmic messengers. The Vera C. Rubin Observatory, scheduled to begin operations soon, may detect hundreds of interstellar objects over the next decade. But perhaps most importantly, The 3I Atlas event has demonstrated that interstellar objects can be far more than passive chunks of ice and rock. They can be active participants in stellar system dynamics, capable of influencing solar behavior and creating electromagnetic phenomena that affect entire planetary systems. This transforms our understanding of what it means for an object to be interstellar, from simple wanderer to active agent of cosmic interconnection. The journey of 3I Atlas through our solar system will continue long after it disappears from our telescopes. After the March 16, 2026 Jupiter encounter, the comet or its fragments will begin the long journey back to interstellar space, carrying with them whatever changes resulted from their encounter with our Sun. In a sense, we are returning modified matter to the galactic medium, completing a cosmic exchange that began millions of years ago when this material first condensed around another star. The trajectory calculations show that 3I Atlas will require approximately 40,000 years to reach the distance of the nearest stars. During that journey, the comet's remnants will continue to experience gradual modification from cosmic ray bombardment, interstellar dust encounters, and the weak gravitational influences of passing stellar systems. By the time these fragments arrive in another stellar system, they will carry within their atomic structure the signatures of multiple stellar encounters, creating a cumulative record of galactic chemical evolution. As we prepare for the November reemergence of 3I Atlas, we stand at the threshold of a new understanding of our place in the cosmic community. We are not isolated inhabitants of a single star system, but participants in a galaxy-wide network of matter and energy exchange that connects all stellar systems through the wandering messengers that travel between them. The story of 3I Atlas will not end when it disappears from our telescopes. It will continue as part of the larger narrative of galactic evolution, cosmic chemistry, and the deep connections that bind all matter in our universe. We have been privileged to witness one chapter in this cosmic story, to observe directly how matter from another world interacts with our own star, and to glimpse the profound interconnectedness that underlies the apparent emptiness of space. The bigger question that 3I Atlas has forced us to confront is not just about this one interstellar visitor, but about the nature of cosmic community itself. We are part of something larger, more connected, and more collaborative than we ever suspected. The universe is not empty space punctuated by isolated stars, but a vast living system where matter, energy, and information flow between worlds in an eternal dance of cosmic evolution. Watch the skies in November, when 3I Atlas reemerges from behind our Sun. You'll be witnessing not just the survival of an interstellar messenger, but evidence of the deep connections that make us all citizens of a galaxy where every star system touches every other through the ancient wanderers that carry messages between the worlds.